Your first one. Yeah. In the head.
Okay, take your seat. Take your seat. We are going to restart, and now we leave phenomenology. We go deeper into the detectors, which of course are anyway very much related to what we want to discover. So to the introduction made by either Marco Cirelli and Marco Pallavicini on dark matter and energy. Giuliana Fiorillo is the speaker. She already introduced herself yesterday. Just as give you a flavor, we were together in the astroparticle committee for many years, and she was at the time the national coordinator of that side. I had the same role for Xenon, so we were good competitor and I think good colleagues, and this is what I like also of the way of working inside INFN and inside our scientific environment. So Giuliana, please.
Thank you. So I will go deep into the details, the technical details of these non-liquid detectors, which are used both for neutrino and dark matter physics. I know that in the audience we have many experts of this technology, so most probably I will repeat things that you know. Anyway, I will try to give a cut, let's say, a perspective towards the future, the possible developments. Maybe this is more interesting for you. Although I need to say that, okay, that I have heavily used materials that I didn't prepare myself. So I have to thank Laura Baudis, which many of you know, and who is in the Xenon community, for allowing me to borrow her slides, and Roberta Calabrese, who edited most of them to update them. So the materials are there. I hope we start a conversation and we go into the details that you are more interested in. I will start with the basic microphysics of novel liquids. So in particular, of course, the scintillation process, which is one of the areas where many developments are focused, but also the ionization, and in fact, and on in general on the use of these two signals in order to determine the particle, to use these novel detectors as particle detectors. One specific subject of interest is the energy calibration, because you heard that most of the physics is done in different energy ranges, very different. So there is a quest for using this novel detector, push them towards very low energies. It's impossible to remove. Okay. Maybe. Okay. And then I will give you, for this first part of the lectures, an overview of the technologies which I used. In the second part, I will attack the dark matter direct detection, which was not covered by Marco, and give you an overview of what's going on in the neutrino area, hopefully, if I manage. Okay, so let's start from the basic properties of these noble liquids. As you know, noble gases are special because they are at the end of the periodic table, which means that they do not mix with other components. They do not are not very reactive. And that's good because in this way you can obtain very high purities, which is one of the requirements of these detectors in all fields. In addition, they can be obtained from air, liquefying air. This is true to a certain extent, because if you want very large quantities of these materials and very pure quantities of these materials, we will see that you need also to look elsewhere, not only in the air. They need, in order to have large masses in the detector, they need to be liquefied, and they liquefy at very low temperatures. This is usually, we speak about this range of temperatures, 183 Kelvin for xenon and 89 Kelvin for argon, and of course 4 Kelvin for helium, as cryogenic. Actually, this is medium cryogenics, because if you speak with cryogenists, then they want to go below the Kelvin. So this is not very tough, let's say. We know how to do it, but you need big lengths in order to treat with these materials. And finally, they have very good qualities as particle detectors. So in particular, they have higher density, of course, and larger stopping power than gases. And as I said, they provide both scintillation and ionization, and can be purified in situ, which you cannot do with solids. For instance, Marco Pallavicini spoke about several solid-state detectors for neutrino physics, in particular for double beta neutrinos or decays and so on. But in that case, you need to have pure material. In this case, you can purify the material additionally when you in the detector. Okay, as I said, because of their ability of providing both light and charge, they have been used since 40 years in all areas of particle physics, in particular for very high energy particle physics, where they were initially studied. One of the founders of these technologies that we will see for low energy physics is Elena Priele, the head of the Zeeman experiments or series of detectors. She was a student with Carlo Rubbia, and Carlo Rubbia was the one that in '77 proposed the use of these materials, both xenon and argon, for low energy physics, particle physics. Since then, a lot of progress has been made, both by our community, the dark matter community, but also in the neutrino community, in order to use them also at lower energies, in particular for the neutrino detection and proton decay, where we nowadays have huge detectors using, in particular, liquid argon. For the neutrinoless double beta decay in the MeV region, so even lower energy with respect to the, let's say, solar neutrinos that are detected with these very large experiments. And finally, for the dark matter detection, where the energy range goes below the 100 keV and is pushed towards below the single keV. So I will focus on, of course, on the low energy part of this technology, and not cover the use of novel liquid detectors like calorimeters. We have calorimeters with liquid krypton or liquid argon used, for instance, at LHC, and we will not cover this. Okay, calorimetry is one of the first applications because these novel liquids provide excellent energy resolution. We will see how. Particle identification is another one, which you can do. I will also cover this either by looking at the energy loss per unit of part, let's say, but also through pulse shape discrimination in argon. They offer also precise timing because they are very fast scintillators. And once you build sophisticated time projection chambers, they also provide tracking and 3D reconstruction So they are complete detectors. They don't need that, you can build a homogeneous detector without anything else, substantially. So that's why they are so widely spread. In addition, as from a technical point of view, all noble liquids are inert, they are not dangerous, they are not flammable, they are very good dielectrics. So you can apply very high electric fields which are needed to drift electrons and collect them. And you can drift these electrons over long distances because the electrons are not attached by the noble liquid. And as I said, you can purify the noble liquid from electronegative impurities. Finally, as scintillators, they are transparent to their own scintillation light, and the attenuation length of light is very long, which means that you can do very large detectors by putting photodetectors all around the volume, the active volume. This is common to all gases, but as a matter of fact, in low energy physics, we use mainly argon and xenon because of their higher availability, the simplicity of procurement, and also because the technologies are very much developed. We have new detectors being developed also with other, like for instance with helium, but I will not probably cover this because I don't have time. So why are these xenon and argon detectors specifically used in dark matter? Because they are very dense and homogeneous detectors for producing huge targets for dark matter, for the direct detection, which was not covered. They provide self-shielding from external backgrounds, and fiduciarization is possible because you can construct the position of the events inside the detector. And finally, as I said, they can be made ultra radio pure, which is probably the most important feature from the dark matter point of view. I already said about the temperature where we have to work. I would just highlight here that the availability of these gases is not equal. Here you see the difference between xenon and argon. I will ask Marco maybe later to tell us what is the current price of xenon, because the cost is very, very volatile. Let's say you can find it for 1,000 euro per kilo and more now, even more. So one feature of the communities, both for argon and xenon, for different reasons, need to collect the large quantities of these gases in order to increase the size of their detectors by starting in due time. Let's say you cannot just go there and procure a large target of xenon. You wouldn't be able to do that because the world production size, let's say, of this material is limited, and there's simply not enough for us to use it. Okay, so it's not so easy, let's say, to procure it. Let's go now into the details. So first of all, how we detect particles. We need these particles to release a fraction of energy, of their energy into the medium. And the energy loss in the noble liquids can be described as a fraction going into ionization, which is this first part here, a fraction going into excitation of the medium, which is this fraction here, and finally, unfortunately, there is always a fraction which is lost to detection for the big detectors that I will describe, because this fraction of energy is goes into the kinetic energy of sub-excitation electrons that are not capable of further exciting the atoms of the medium, and eventually they are absorbed, and so this energy is lost into heat. I will mention that there is a tentative now, a research and development activity in order to exploit also this part with superconductive sensors and measure the energy lost into heat, so that you can really have a full sampling of the energy lost into the detector. But for the rest of this lecture, we will focus on the ionization energy loss and on the energy lost into excitation. So remember, Ni is the number of ions produced. so number of electrons and correspondingly of ions, and X is the number of excited argon, either argon or xenon atoms. How much is EI, that is the energy lost into ionization? We could think of using the average ionization potential, because these are atoms, but these atoms are in a liquid, and so the energy levels are a little modified with respect to the gas. And what's found by experiments is that there is a band-like structure, like in solids, more similar to solids than to gases. So we will use, instead of the ionization potential, the so-called energy gap of this band gap, let's say. And we will define the so-called W value, which is the energy required to produce a single electron-ion pair, as the total energy loss divided by the number of ions. So it's an effective number. It's not corresponding to the either to the energy gap or to the ionization potential. But once you use this W, you can relate the W to the energy gap of the liquid, just dividing by Eg, and you will obtain this formula, where, as I said, this fraction will be very small. So we will try to neglect the energy lost into heat. Certo che è un problema questo. Okay. So the ratio between the W and for the ionization and the energy gap is larger than 1. So you need more energy than what you would need just to create a single ionization on average, because of course you have multiple ionizations in a single interaction. So you have the particle releasing energy, and that produces electrons that then also ionize the medium. So on average, you will need 60–70% more energy to produce a single electron ion. And this takes into account this epsilon fraction that we have neglected. So the effective number for W is around 20 electron volts, where the gap energy is lower for all media. It is minimal in xenon, which is an advantage because you need less energy to produce a single couple, and that means that you have more charge to detect in xenon for a given energy. Also, it's important to take into account the very much different density between the heavier xenon and the lighter argon. And this brings you to an average energy loss per unit path, which is 2.2 MeV per centimeter in argon, 3.5 in krypton, and 4 for xenon. So this is an example in argon where you can see the standard energy loss in the medium expressed in MeV per centimeter, and as a function of the energy, not of the beta of the particles. So you can have an idea of how you can distinguish different particles in argon through their energy loss along the path. So that's a standard procedure which is used everywhere in particle physics, and this can be used also with noble liquids. On the other hand, once you produce these couples, if you don't have an electric field to collect the charge, most probably all electrons will recombine with the parent ion. And this is obvious thanks to the high density of ionization along a track, which will produce a very high recombination, which you can assume is even 1. Actually, all electrons, almost all electrons, will recombine with the ions. Of course, if you apply an external electric field, then it's an interplay between the electric field trying to extract the electrons produced along the track and the local ionization density that wants to produce recombination. And so increasing, you will see that increasing the electric field, you will, this is the electric field expressed in kilovolt per centimeter, you will increase the efficiency in extracting and collecting the charge produced in the interaction. But at very low field, you will not see any electron because they will simply recombine. A striking point here is that electrons do not behave like heavier particles. In particular, here there is an example with alphas, but in the literature you will find similar plots for all kind of ions or fragments, nuclear fragments moving into the noble liquid. And you see that the recombination probability is very different for particles which have different specific energy loss per unit part. And this is something very well known. In particular, there is the Briggs model, which can is very widely used in order to model this behavior. Essentially, the collected charge is less than the produced one. And in order to increase the efficiency, you have a dependence on the specific energy loss of the ionizing particle and, of course, on the electric field. So different particles will have different proportionality constant here, different K. This model wouldn't fit very well these curves along the full range of possibilities, both in the dependence from the E over the X and in the dependence from the electric field. So we have a huge variety of microphysical models to model this phenomena. One which is very good at very low energy is the so-called Thomas Imel model, or also called box model, which assumes a specific structure for the energy loss along the track in a box, and that's why it's called box model. And then models the behavior of electrons inside this box. And this model fits better part of the data. So I'm not going to the details of the models, but later I will go back to this phenomenon of, let's say, quenching, loss of charge along the track. Yes?
Why is it not important for the box model to include this PE, the extra, so if it's in the other
No, no, it is.
expected to be important?
Yes, it is there. It is actually there because this variable here is defined as proportional to the number of ions that you produce. So it is proportional to the update. And all the models that we have here actually are different parameterization of these box models, variations, modifications. They are called modified box model, modified Briggs model. This is a field of research which is still active, let's say. But you will see the different energy ranges fit with different models. So, okay, as far as the scintillation is concerned, many of you have studied at school how it works. It is one of the basic knowledge for scintillators. So once a particle interacts inside the noble liquid, it produces two processes, two possible phenomena. One is the direct scintillation, let's say, also called excitation luminescence. So you immediately excite an atom. The excited atom collides with the other atoms in the medium and forms together through these collisions, forms the so-called dimers that are excimers, excited molecula, formed by two excited atoms. And they are they are one specific feature of the noble liquids because the molecular structure of the noble gases is very different from the atomic one. So once you are in the liquid, you can form these dimers that have different energy levels with respect to the atoms. And that's why when they de-excite, they produce light over the given wavelength that cannot be absorbed by atoms. And then these dimers will de-excite, and when they do it, they will dissociate and go back to the single atom structure and produce unfortunately, vacuum ultraviolet photons, that is very ultraviolet. So much that this can be a problem in the detection, because as you know, almost all photosensors have protective layers. Let's think to a photomultiplier. It will have a window made of glass or quartz, and that glass or quartz will be a filter towards very short wavelengths. So for xenon, it's a minor problem, but for argon, this is a major problem, because the wavelength of argon is 128 nanometers, much below the cut of the quartz, or there are very few materials that can be transparent to these very short wavelengths. Okay, another thing that I want to point out is that these excited levels of the dimers come in different spin states. So you have singlet and triplet states, which are very different behaviors. In particular, they have different decay times, different lifetimes. And this means that according to how many singlet states and how many triplet states you produce in the interaction, you will be able to use the different shape of the light signal produced from the excitation to identify the particles that are producing the light. This will be shown in a moment. Okay, so what I described is here. Let's assume that you have an interacting particle. The first thing that the particle will do is hit an atom in the liquid, so it will produce a recoil. And the recoil can be either produced by electrons of the atoms or even by the nuclei themselves. This recoil will move in the medium and produce additional ionization and additional excitation. We have seen that the ionization signal produces ions and electrons that we want to collect. So we will apply some electric field in order to collect these electrons. If we don't, the electrons will recombine with their ions. But as these ions also produce dimers, let's say, which are made of ions, so a molecule of argon plus, then the recombination brings you into a excited states of high excitation of the atom of argon. And this excited state, again, will interact with the excited argons that are in the high density region of the track and produce the excited dimers, which will then decay through light. So this means that if you don't collect the electrons, as I said, they will all recombine, but in doing so, they will produce additional light. So we have two different sources of light, and the second process is the recombination luminescence. So the direct excitation is this process. The secondary excitation is the recombination. So recombination is a specific microphysical aspect of the interaction of particles in the noble liquids that is very, very important. If you want to really measure all the energy loss of the particle, because you want a high energy resolution, then you will need to know exactly how this recombination process behaves. Unfortunately, it's not so easy because, as I said, there are processes that occur in between. In particular, these excited species can collide with each other, and in doing so, they will lose part of the energy. So this is called quenching. Fraction of the energy that would go into light, for instance, because of the excitation process, will not go into light, or not in the same quantity, because two excited atoms can combine a very excited dimer that then will decay without emitting any photon. So you lose light. Of course, here you have again an ion and an electron. So you will start back from here and you can produce additional light, but that will be one photon, while here you have two excitons. So you have lost here in this process half of the potential light to be produced. This phenomenon of losing a part of the signal, potential signal, is called quenching. And it is the most difficult item to discuss in this physics because it's, of course, requires a very good modeling of the atomic physics that is involved. Another process that also makes you lose a fraction of the signal is that some electrons in order to recombine, they have first to thermalize, to lose some energy and arrive to the region where they can recombine with their ions. But if they thermalize far from the ions, then they escape. Escape recombination means escape detection, and this means that we lose energy. So that's another quenching phenomenon. And this, which I explained, are called electronic quenching. It's a loss of energy that would come out as scintillation light proportional to this ionization and excitation phenomenon. This specific process is called B-excitonic quenching. The reason is that there are two excitons that are involved in the process. It's also called pending quenching. And as I said, it makes you lose a lot of energy, so it's very relevant. So concerning the other characteristic of this scintillation signal, as I said, the wavelength is a problem. I spoke about argon, but also liquid neon has got a very short, very short wavelength, and xenon slightly larger. This makes better xenon for detection of scintillation light, so another quality of xenon. It seems that I'm advertising the activities of Marco instead of mine. I will come to argon later. Because the quartz windows are transparent to this light. They are just below this level, and so you can use standard photomultipliers. Another good reason to use standard photomultipliers in xenon is that the temperature of liquid xenon is 100 degrees above natural. So it's cryogenic, it's just minus 100 degrees, essentially. So not so much cryogenic. If you put photomultipliers into a liquid, they will work, standard photomultipliers. They will have a lower efficiency because of resistivity problems on the photocathode, but now there are specific photocathodes built to cope with this problem. Then you will have lectures on the photosensors at the end of the week, so I will not dwell too much on that. But just to let you know that what is true for xenon is not true for argon. If you put standard photomultipliers or even cryogenic ones with this new photocathode at minus 200 degrees, which is the temperature of argon, they will show you many problems. A huge mess of problems, going from fatigue effects to light emissions. They will be lamps. They will produce their own light. And essentially, this made the community abandon photomultipliers for this reason. Okay, finally, let's look at the pulse shape. As I said, you have two possible excited states producing this light. One is a singlet state and the other one is a triplet state. And as a result, all noble liquids, like noble gas, show two components of the light emitted. One very fast. I think that you should look at this curve here. You see that there is a fast component, and then after a while, you see also the slow component. This is visible for alpha particles. It's not visible for electrons in xenon. This is a plot concerning xenon. So electrons only show the slow component, while alpha also show the fast component. This, in theory, would be a good tool to discriminate between electrons interacting in xenon and alphas interacting in xenon. Unfortunately, the time constants are very near, 22 nanoseconds slow component for alphas and 45 nanosecond slow component for electrons. So this is, there have been attempts to exploit this, maybe there are still, but it's not widely used because you don't have very high discrimination power. This is not true in argon, and here it comes the first good reason to use argon is the difference between the singlet and triplet state decay constants. The fast one is as a time decay constant of 7 nanoseconds, and the slow one is 1.5 microseconds. So they are orders of magnitude, 3 orders of magnitude different, and this makes a huge discrimination capability between the electrons or minimum ionizing particles or heavier fragments like alphas or heavy nuclei. So this is the basis of the pulse shape discrimination in art. So once you have, yes.
Just a quick question about this slide before. With general purpose scintillators, it's like the other way around, right? That you have.
Yes.
I was just wondering.
Yes, good catch. It's true. Normally, you have the opposite situation in lipid scintillators. The fast decay is for electrons, and the slow one is for, yeah, I don't know why there is this difference. There have been studies trying to connect the population, the mechanism that populate either the singlet or triplet in novel liquids, but they are not so much developed. Anyway, it's true. Remember, it's the opposite of lipid scintillators. Okay, so once you have excitations and ionization, you can sum up both of them. For instance, if you don't collect electrons, you will simply at the end get all excited atoms, both for those which were born as ionized atoms and those that were born for direct excitation. And so you can define a different W value, which is simply the fraction of total energy loss divided by the number of total quanta produced, okay? And this value can be expressed in terms of the W that we have defined before, the ionization W. If you make some math, of course, you will obtain that the W for photons is a little bit smaller than the W for ionization, and the ratio is depending on this fraction, Nx over Ni. So there have been many attempts to measure this fraction, and I have looked back into the literature, which is very old also. There is no common value. You can assume it's more or less 20%. Okay? So it's more or less 0.2. Many measurements confirm this value for argon. There are more complicated measurements for xenon where this number can vary. It's a very difficult measurement because you have to actually measure Ni and Nx, so collect all the electrons with the electric field. Then you will have dependencies from the electric field that are difficult to disentangle from the measurements. So that's why these numbers are at the end. You fit your data with a model and you try to parameterize the dependence from these numbers. Okay? But for the moment, let's assume 0.2. Then the number of photons will be given by the number of directly excited atoms plus the fraction of the ionized atoms that have actually recombined. This small r is the recombination probability, let's say, and it's another unknown that depends on the E over the X and on the electric field, of course. And finally, the number of electrons that you will collect will be given by the initial number of ions produced multiplied by 1 minus R. You have to subtract the electrons that you have lost due to recombination. Oh, so all this, just to show you this plot, which is fundamental. The light signal and the charge signal, so charge and light, are complementary. They are highly correlated. If you don't extract charge, you will see all that signal into light. If you do have an electric field and you extract the charge, what you don't see in light, you will see in charge. So it's extremely important to both collect charge and light. And once you do, then you can sample the full energy loss of the particle, and you can expect that the energy resolution, which is one of the most important benchmarks of a detector, will improve. Okay, so the total energy will be given by the sum of charge and photons. And the calibration constant will be this new W that we have defined in the previous slide. So from now on, I will drop the subscript, and the W value, which is our unit of energy, how much we need to produce a signal, will be simply W. Okay, so this W is a little bit better than the one only for charge. It's 19.5, and is a very stable number in argon, in liquid argon. And it is a little bit less stable in xenon. It's around 13 or 14 electron volts. There are different measurements again. So this is a number that is still not known very well. Okay, so that's how much energy you must employ to produce a single quantum of signal, either charge or light. This slide is quite difficult. I will not dwell too much, but just to show you, I said what is the process that produces substantially. Okay, let's look, for instance, at liquid argon. 100% of the interactions are divided between 64 recombination process. So the light that you produce is 64% coming from recombination and 36% coming from direct excitation. Okay, so that's the fraction. But this is for electrons. But in both cases, only a small fraction goes into singlet for electrons, and the vast majority goes into triplet. So the light produced will be essentially coming from triplet. But you know which is the ratio of fast to slow component for electrons. In xenon, these two numbers are more or less the same, 70% and 30%, but we don't know exactly which fraction of the recombination light goes into singlet and which goes into triplet, because for electrons, we don't see the fast component. The recombination is not well known in xenon because it's too fast, it's competing with the decay. While in argon, you have this slower decay, 1.5 microseconds, that allows you to study the combination factor, which is faster with respect to the direct excitation. This is true for electrons. Of course, if you go to alpha, where most of the light is prompt, then you don't see anymore the difference between recombination and excitation. So you cannot study this, and you will only see the fraction of triplets formed and the fraction of singlets shown. This is true both for argon and xenon. Anyway, you can go back to this slide later. The reason of the difference between electrons and alphas, as I said, I don't know. But what is known is that alpha are 100 times more ionizing than electrons. The density of ions along an alpha track is 100 times higher than the density of ions around an electron, high energy electron track. So that's the concept I want to stress here, because I would like to introduce you to the quenching phenomena. Okay, so this is another very well-known and old plot. There have been a number of studies. What do we have here? We have the so-called LET, linear energy transfer, which is nothing else than the dE over the x, the energy loss along the path of an ionizing particle. And of course, it does not correspond to the energy of the particle that is for electrons. So this is liquid xenon, but it's very similar in argon. For electrons, higher energy electrons will lose less energy along the path, and lower energy electrons will lose more energy along the path. For recoils, that is heavier nuclei that are moving in the liquid, of course the opposite is true. Lower energy lose because we have the Lindbergh theory, you remember the area of the Higgs theory. When the nucleus is low, then it's inverted, the reasoning, and for lower energy, you have lower energy loss, for higher energy, you have higher energy loss. Okay, so if you now test your medium measuring how many photons you produce per keV of energy released, it's not a single number. It depends on the nature of the specific length linear energy transfer of the particle you are studying. So electrons, fast electrons are here. They give you a given light yield, order of 40, 50 photons per keV, which is, by the way, I didn't mention before, one of the highest throughput with respect to scintillators, standard scintillators, so very good scintillator. On the other hand, if you go to a medium range, let's say 10 to the minus 2, 10 to the 2, 10 to the 3 MeV per gram per square centimeters, you obtain a maximum of 70 photoelectrons per keV. And then when you go to lower density, you obtain less because there are electrons escaping the recombination, as I said before. So this is why the number of photons is less than the maximum number that you can obtain at lower length. On the higher side, where the length is much higher, a different phenomenon. Also, you get a lower signal, but the reason is different. The reason is nuclear quenching, in addition to the excitonic quenching, which I mentioned. So here, which particles produce such a high density, such a high linear energy transfer? Only have heavy fission fragments or heavy nuclei. And these particles are very slow. And when they are so slow, they don't interact with electrons, they interact with nuclei. So they are like balls hitting other balls of the same size, more or less. And they lose a lot of their kinetic energy in just vibrations and heat. And so a larger fraction of the energy is lost in these phenomena, which we have completely neglected in the previous description of the phenomenon. So this is called nuclear quenching, and it's a phenomenon that you only find for heavy nuclei. The same situation is in argon here. So electrons are here, then you have this plateau with a maximum 50 photoelectrons per keV produced, and then again, heavier fragments produce less specific light yield. So we have to calibrate our detectors with different particles because there are quenching effects depending on the identity of the interacting particle that is producing the ionization, not only on the detector properties like the electric field you apply, but also on the nature of the particle. Of course, this is also the basis of particle ID. So let's, what time is it? Why not? Let's look into quenching. I think I have to hurry up a little bit. Okay, so let's go back to the global picture. We have electron recoils produced when the particle hits an electron, and nuclear recoils when the particle hits the nucleus of the atom. And these two different interactions will produce a different ratio of excitation to ionization. They will both produce both kind of phenomena, but in a different ratio. And this will bring to a different ratio between light and charge for all the reasons that I have explained until now. In addition, of course, for nuclear recoils, you also have a fraction, consistent, large fraction of the energy which is lost, simple loss. Okay, this is exactly the same thing that I showed before, so the same plot. This is the so-called quenching factor, so the efficiency in producing this quanta, light quanta in this case, with different particle species, both in xenon and in argon, very similar situation. But really in this slide, I want to stress that these phenomena require that we subdivide our energy loss in a slightly different way. Fraction of the energy lost by interactions on electrons. This is the electronic stopping power, and it's not the total energy, but just a fraction of it, that is B0 that we were speaking about. And the elastic collisions with nuclei that take away a different fraction, another fraction of the energy called nuclear stopping power. So in general, the nuclear stopping power is lost. And what you get is only this fraction of energy. So the fraction of total energy loss is called the quenching factor. Of course, it's less than 1. And the total quenching factor for electrons will only be due to electronic quenching. For nuclei will be the product of 2 attenuation factors. One is due to nuclear interactions, and the other one is the bi-excitonic quenching that we had already seen. So the total quenching will be the product of the 2. Okay, so we have many models also to describe this quenching. I understand this is a little bit boring, so I will go a little bit faster. And these models fit well generically many solid state materials. Here is the example of the Lindard theory for silicon. I will skip this. Okay. If you apply the same Lindard theory, the same model, you don't fit noble liquids. It's okay in silicon, but noble liquids at higher quenching with respect to silicon, and it's not fit, so lower throughput, lower signal. And it's not fit by the Lindard theory. So that here again, you have many models, but if you at the end sum up the charge signal and the light signal, at the end you manage to recover a behavior which is very similar to the Lindard theory. And now you can see that if I only apply a single factor here to the total energy, so for an electron recoil, the energy is lost into photons and charge, and the factor of proportionality is called W. That's what I have described until now. For a nuclear recoil, you have to multiply for a factor, a quenching factor. And this quenching factor is well described by the Lindard theory. So at the end, the story is, if you calibrate a novel liquid detector, remember that you will need 2 calibration curves. One for electrons and MIPs, meaning ionizing particles, and another one for nuclear recoils. There are models that fit well, but you need to know that your calibration will differ for the different particle species. And that's what we did. So, yes.
Sorry, I have a small question. I know that Lindard model sometimes for like lower energies is not confirmed. Like, was there like a quenching campaign in argon and xenon?
Yeah, I skipped all the history of the many years, 20 years of quenching campaigns and fighting among the communities that found different things, because it's, as I tried to explain, a very delicate issue that of quenching depends on a lot of factors. Electric field, your detector, your collection capability, and so on, that mix up and are entangled together. You have to disentangle the different factors. At the end, it comes out that if you use the total energy variable, which is some charge and light, you can fit with Lindard models. Now the situation is much less competitive, people agree. And so this is the final result. So that's why I skipped all the story. We have a calibration for argon. This is provided by the Duckside 50 experiment. And we have a calibration for xenon, which agrees among the different xenon experiments. This one is from LUX, but it's not different from the one from xenon or other experiments. So we now have an agreement on this and a model or a set of models. Just to let you know that the experiments that have done this have made an history, let's say, and they were all based on this concept that is, let's use neutrons as the source of nuclear recoil. So you produce neutrons, you make them hit in your detector, and then you measure very accurately the kinetic energy of the outgoing neutron. As this is a very simple scattering, this kinematically closes the reaction, and so you know exactly the recoil energy of your recoiling nucleus. And in this way, with similar experiments done by many, many people, at the end you see how many experiments here from all the community, they all fit the same model. So finally, we have an agreement here, and this agreement is evident in the NEST package, which you might know better than me, so, yeah, because you are younger. All this knowledge has gone into a package simulating the noble liquids. I have stolen slides also here. As you see, NEST allows you to model your detector and to model the microphysics inside the detector, excitation, ionization, heat, energy loss, recombination, the excitation, and quenching. Everything is inside NEST. It is heavily used by the community, more for xenon than for argon. But it reproduces data both for electron recoils and nuclear recoils, and also alpha and protons, which are on the in between. And I think that maybe here just I would like to flash a couple of numbers. We have charge yields for electrons and for nuclear recoils predicted and simulated by NEST as a function of the energy and as a function of the electric field. All these lines are for different electric fields. So powerful tool. And we have the same thing for argon and xenon, and for light and for charge. So all these predictions perfectly fit the data coming from all the experiments. Okay, that closes the issue of microphysics in our detector, and I can switch to detector physics. That is, what are our problems in exploiting these signals that are produced by either electron recoils or nuclear recoils. Any questions on the previous? No? Okay. So one detector issue is collecting the charge, because as we have seen, even if we just let the charge recombine, we will have escaping electrons. So it's better to collect charge in order to have a higher resolution. This is well known. But as Icarus demonstrated, I was not here when Marco Pallavicini had his lecture, so I don't know how much he told you about the Icarus dune, not much, okay. Anyway, this is a very old slide. I took it from one talk that I gave in 2004. And that was the period when we ran the Icarus detector, 600 tons lipid argon at the Gran Sasso laboratory. Now the Icarus detector is at Fermilab. It was completely refurbished. It's doing sterile neutrino physics, as you have heard from Marco Pallavicini. But this is a picture of the old Icarus detector, not very different from the new one. It's a big detector with a cathode in between and anodes on the sides. So electrons drift in the electric field generated in these two drift chambers, to the right and to the left of the cathode. Okay? And the anodes is made of different orientated wire planes that can see the electrons, that measure the electrons both by induction while the electrons drift and by collection once they arrive at the last plane. Okay, so they measure the electrons. Of course, this is a huge detector. It operates in a high energy range, let's say above a few MeV. But the basic physics of the detectors was tuned on Icarus in over 30 years of R&D. So let's tribute to the Icarus people what they did, because, I mean, if it was not for them, we would not be here speaking about that. So most important, the drift velocity of electrons in lipid argon for electric field of the order of the kilovolts per centimeter, both below and above this number, is very well known. It's around 1 millimeter per microsecond. So it's a slow drift with respect to the scintillation light that is produced over nanometers. It has a very well-known dependence from the electric field, the velocity. So this means that you can use this knowledge in order to measure where the electrons were coming from, because you just need to wait the time and you convert through the velocity, knowledge of the velocity, time to position. Okay? But you have to drift in these huge detectors these electrons for many milliseconds, because this is 1 millimeter per microsecond, and you want many meters drift. So you have to have lifetime of these electrons need to survive in your detector while they drift for many milliseconds. And this is not easy because, okay, that's a very pure material that does not attach electrons, argon, like xenon, but you can have a single oxygen molecule in your huge detector, even in part per billion or per trillion, that will attach electrons. So what's the effect of this attachment? It was studied and it was demonstrated that you could have purification techniques. So you continuously remove electronegative impurities, and this allows you to increase the electron lifetime from the starting few hundred microseconds to several milliseconds. This was already demonstrated with Icarus, and now it's demonstrated everywhere. You can sorry? You can go above dozens and tens of milliseconds. Other effects that have been studied are the diffusion. While the electric charge moves, the direction of these electrons will be a little bit modified by the diffusion effect in the drift. And this was also very well studied, and also its dependence from the electric field through this velocity, which is proportional through the mobility to the electric field. Okay, let's look at the purity issue. So electrons can get attached by impurities. The standard impurity, as an example, is the oxygen, but they all behave in the same way. The signal that you get at the end of the drift will be reduced, attenuated with respect to the initial signal through a time constant, which is called electron lifetime. And this time constant is inversely proportional to this concentration of impurities. So the higher the concentration, the smaller the time constant. And so through some coefficients that have been studied and have been related to a standard one known for oxygen, which is this one. And here you see the effect of different impurities. For instance, this oxygen is here, and water is here. And this is, I think, in argon. And of course, they depend on the electric field. So this means that you have to reach purities in order to have attenuation lengths greater than 1 meter. You have to reach purities of below part per billion. And in order to do that, you use huge plants for purification of both argon or xenon. These plants essentially contain filters, and the filters can be used either in gas phase or liquid phase. So in liquid phase, many huge detectors use purification in liquid phase. You have pumps pushing the liquid out of your container, going through these filters and then back into the detector. Okay, that's one way. And this can be done through pellets, substantially, that absorb impurities. Or many, for instance, in that matter, we use much more. The gas purification, because they are more effective, then you have to evaporate part of your liquid, extract it in gas phase, pass through a getter, usually high temperature getter, which attaches all the impurities, and then liquefy back your system. So these huge plants are visible. For instance, if you go and visit the xenon detector in Grazzasolo Laboratory, they have a wonderful a building from which you see, because it's a glass window building, all these nice plants, but they are everywhere, both in the neutrino detectors and in the dark matter detectors. You need them in order to operate. If you take a small detector with argon and you try to look at these signals that I've been speaking about, most probably, if it is not really small, you won't see anything because of the impurities of the commercial argon. So you need to know how to purify it. Okay? It's one of the tricks, let's say. In order to measure the purity, you can use a small drift chamber. Actually, it's a TPC. You use an ultraviolet lamp hitting with high energy photons on a photocathode, producing electrons, and then having these electrons drifting into a known electric field. At that point, you know how long is the drift, and you know where the electrons are starting from, so you can measure the attenuation of the signal along the drift. And like this, it is sufficient that you measure the pulse at the anode and the pulse at the cathode, and then you make the ratio, and that will give you the lifetime of the electrons. So if you put such a drift chamber inside your huge detector, it will have the same xenon or the same argon, so the same purity, more or less. Now I will say a word on more or less. You measure the purity there, and you got a number without having to fight with reconstruction in your huge detector. I said more or less, because of course in huge detectors you can have concentrations of impurity due to the flow of the liquid, and these purity monitors will be in specific places, so it's not exactly so easy. But if you have many, for instance, in the Joule detector they have many, then you can do a map of the purity in your detector. Okay. So this is a picture of an actual detector here, and another picture, one for carbon and another one for cleaning. They're exactly the same. Okay, do I have time? Yeah.
40 minutes.
Ah, okay. And how many slides? Right, well, perfect. 2 minutes per day. Okay. Self-regulation. But give me a moment. Sto morendo di caldo. Okay. Ah. Okay, energy calibration. Let's go back to our single cartoon of the talk. Yes.
I don't like to know the bigger parts, so maybe in their perspective.
Yes.
Now, which are the, let's say, radioactivity levels that usually are required for that kind of experiment?
So for the drift, which, so, because you said radio purity, while I have been speaking about purity, and it's completely different. For the drift, it depends on the size of your detector, and you can just rely on the numbers that they've written. In order to do, let's say, of the order of 10 centimeters, so if this is the size of your detector, 1 ppb is sufficient, and then it scales accordingly. So you have to go below fractions of ppb for meters detector, okay? For the neutrino physics, where the drift can be 4 meters, 6 meters, now 6 meters in the protodune vertical drift, then you need even higher purities. Okay, for the radio purity, that will be addressed in the next lecture, and it's a completely different story. Much, much less than this, okay? Okay, so this was the cartoon showing the physics that is coming. So we have energy loss in ionization, energy loss in heat removal, energy loss in scintillation, and you sum everything. Now you are in your detector, so this is exactly the same formula as before, with our new W value, which can be given by the numbers of the table I was showing you before. You take into account all the quenching factors, okay? And at the end, you must convert these into signals. So your signal in the detector will not be number of electrons and Q or number of photons and pH. You have to measure that number and that both for electrons. Oops, sorry. What am I doing? Okay. So when you measure, and we will see in the next lecture how we measure, but you will have a signal. A signal will be an electronic signal, okay? And let's call S1 the signal which is proportional to the number of photons produced in your detector that you have to calibrate. As it is proportional to the number of photons, in order to get NPH, you have to multiply by a constant, which is your calibration constant. Normally, we use the term G1 for the calibration constant of light. Fortunately, we all do the same, both in xenon and Arduino community, so it's a universal language. Then you have a signal proportional to the charge, and that will be a different proportionality, because your detector will measure charge in a different way with respect to light. And so we call it G2. And so this formula becomes this one. G1 and G2 are normally measured in terms of photoelectrons per quantum, because we usually convert also the charge signal into a light signal. So at the end, it's always photons per quantum. Okay? And as you have photosensor, it will be photoelectrons per quantum, because you also have to convert the photons in the detector. The typical values are 0.15 photoelectron per photon. So remember, you only have 15% efficiency to detect one of those 50 photons per kV of energy released in xenon, 0.11 in lux, 0.16 in dark side, more or less with that 10, 20% maximum if we are good. Because we are, no?
Yeah.
For the charge, which we convert into light, we have 10 photoelectrons per electron, 12 per electron, 23 per electron, because I'm better. No, this is by design. Normally you tune this conversion factors. It's easier with the charge, so it's by design. It's not, higher doesn't mean better. Okay? Here, yes.
Is this proportionality also valid at very low energy?
Yes, I would say yes, but for the problems of the quenching, remember that you have also the quenching. I'm not considering here. Okay? You remember very low energies? Yes, because I will show you now the dependence from the energy. These are calibration constants that describe the energy calibration. But you have a dependency from the nature of the particle, which is taken into account in the quenching factor that I've shown you before and needs to be multiplied here. Okay? So, yes, your question is yes. So this is what you measure. Perché si è alzato la donna? Okay. So you measure, you use a calibration source at a given energy, okay? And you measure how many photons you obtain and how many electrons you obtain in the signal through your S1 and S2 signals. And these plots show S1 versus S2. Okay? What you see is that, okay, forget about this tail, which is due to the fact that the source is not completely pure. Look at the Gaussian, which is here, no? It's a bidimensional Gaussian with a different resolution in S1 and S2. And that's because the two measurement methods are different. And this is true in Xenon 100, and this is true in another Xenon experiments looking into a higher energy range. So different source and different range in S1 and S2, but they both measure the same thing. So you see that you obtain this typical plot that is, and what is typical in this plot, that you have a strong correlation between an anti-correlation between S1 and S2. And that's because the total energy, S1 plus S2, is constrained by the energy source, by the source energy, sorry. So this anti-correlation is a fundamental property of these detectors that measure both charge and light. And once you exploit these, that is, you sum, as we saw in the previous slide, S1 plus S2 normalized through the calibration constant, then you obtain the resolution in your measurement of the energy. So if you look at this plot to the right, in EXO, for instance, you can see the two Gaussians that you obtain if you only consider the scintillation light or only consider the charge light, which are spread, have a wider resolution, and the better plot, much better plot with a much better resolution that you obtain once you sum charge and light. Similar thing is done in LUX, where the resolution is shown as a function of the source energy. So for different energies from 0 to 700 kV, and is also fitted with a standard function perfectly fit in the data. Okay. This plot is called Doki plot. Doki is one of the masters of argon and xenon techniques. He has studied practically everything, and so you find his name everywhere. Most of our knowledge comes from his studies. So this plot is called the Doki plot, and it can be used to calibrate your detectors from many points of view. For instance, you measure S1 and S2, and you try to measure the charge yield and the light yield as a function of the different energies. From a linear fit, you extract G1 and G2. So this is a method to calibrate your detector, to measure your G1 and your G2. Be careful. While I said that G1 is essentially your collection efficiency for the photons, and it's around 15% globally. For S2, it's a little bit more complicated because there is also inside the conversion from charge to light. It's expressed in photoelectrons per kV. Okay, but we will come back in the next slide. So the actual data here you see, for instance, in xenon 1 ton, different possible sources with different energies. So here you are around MeV, and here you are around 40 kV. So this answers to the previous question. So for different energies, they all lie on a line with the same G1 and G2. This is the answer to the previous question. And the measurement here for xenon 1 ton are shown here, 11 photoelectrons per electron or 0.14 photoelectrons per photon. But you can also use the same plot to measure the W, for instance, because you can extract the W. So if you have an independent way to measure essentially G2, which is your degenerate variable with W, and there are independent ways to measure G2. I will not go inside, but if you have single electrons, you know that they are 1 electron, so you know what is the calibration factor. So G2 is easy to calibrate. You know these, and then you use the Doki plot to extract the W from this formula. In order to do this, you can use different energies, but you can also use different electric fields, because remember that we have charge signal changing with the electric field. So if you use the same source but different electric fields, also the data will be distributed along this line, and so you have met several tools to measure this. Okay, I am almost done.
We have half an hour.
Okay, either we can devote it to discussion, or I can go to the next. Okay, so some challenges to construct your detector. So I've spoken a little bit about cryogenics. I said that we need to do purification system, but while I was describing the purification system, I said that the most effective, in particular for dark matter, where you need very high levels of purity, are, and the reason is that you want to measure the single electron. In neutrino physics, you have many electrons produced along a track. You can afford losing some electrons. In dark matter physics, you want to see single electrons because you want to go to low energy. You cannot afford losing a single electron. So you need higher level of purities. Okay? So what we do is we evaporate fraction of the liquid and we purify it through getters, and then we liquefy. So our system, our cryogenic system needs to liquefy, purify, and recirculate the liquid. These are the three functions, and usually in order to do that, I have no slides in detail, but there are heat exchanges. You have to try to recover the heat loss of you are producing gas through the heat that is produced in the detector, and then you recuperate because you have cold gas and you take this heat in order to liquefy it back. Then you need detector materials which are compatible with low radioactivity imputed requirements. So that's the problem of the dark matter searches. You need very low levels of radioactivity. So all the materials in the detectors must be pre-selected and pre-measured. You have to measure the materials to know the level of radioactivity. And of course, you have to pre-select the materials in order to have very low levels of radioactivity. Then you have the problem of the intrinsic radioactivity. If you have your target, which is radioactive, then you have a problem. So isotopes of both argon and xenon can produce local radioactivity. Actually, xenon is not affected by this problem. Xenon is Xenon is most affected by another problem, that is the contamination in krypton and in radon. The first one is in the distillation process. So you need to have specific purification techniques for krypton, which xenon experiment does, for instance, with also very, very high efficiency. While the second one, the radon 22 emanation and diffusion, is a common problem to all the matter experiments, not only non liquids, because radon is in the air gets in the materials, and the materials then outgas this radon and produce. And the radon by diffusion into the liquid. So also there you have to remove them, and we have reached, I will show you in the next lecture, very, very low level of radon now in xenon in particular. While argon is a huge problem, because if you take argon from the atmosphere, the vast majority is argon 40, which is a stable nucleus, but cosmic rays produce, hitting the argon, they produce argon 39, which is a beta emitter, the case. And in the case, producing electrons in the 100 degree. So we have a huge problem. We have to reduce these electrons, this contamination of argon 39 in liquid argon. And what we do, as I will show you, we extract it from underground. This is not an invention. It's the idea of using natural gas reservoir to find radio-pure materials. For argon, it required very long R&D and the construction of industrial plants that are capable of extracting large quantities of this radio-pure argon, but we managed. Then we have another problem, the light detection. I already mentioned the difficulty of using standard photomultipliers at low temperature. Another problem is that of having ultraviolet sensitivity. So as I said, again, this is more difficult in argon than for xenon, I already explained. For this reason, in liquid argon, we use wavelength shifter. So material, we deposit material on all the surfaces internal to the detector that absorb the ultraviolet light at 128 nanometers, and emit it back in the visible region at 420 nanometers, and then at that wavelength, all the photosensors are sensitive, so the standard photosensors. So that's solved, but you have the further complication of having this wavelength shifting material in the detector. And finally, the contaminations can also absorb light, so there is a problem. But if you purify for the electrons, then you are also pure for the light. Here I already spoke about that. The last last challenge is connected to the electric field. All the plots that are shown were with fields in the region from 100 volts per centimeter to a few kilovolts per centimeter for all the novel liquid detectors. But bringing the voltages at the cryogenic system, so inside the cryogenic, the high voltages that you need in very big detectors in order to have even low fields like this is a problem. It has been a huge problem in the past, that of designing and inventing fit-throughs, that is connections between the room temperature and the cryogenic temperature, that were capable of doing this without allowing for sparks and discharges. Maybe Marco can also say a word here.
So
It's a huge problem, not completely solved. In fact, many experiments still need to operate with very, very low voltages, and this means slower signals, more pile-up and problems. So this is one of the regions where we still need R&D. The technologies, I see that you are very tired. So these are only cartoons. It's just an introduction to the next lecture. You all know more or less what are the technologies for the detectors. Very simple, single phase, a big sphere with a novel liquid inside and photosensors everywhere. Simple, no fit-through, no high voltage, no problems, no headaches, no surprises when you go in the operation. Even the photomultipliers can be far away from the cryogenics. You can just put it, can have light guys and photomultipliers in a safe region from the radioactivity point of view. So very simple, with a lots of drawbacks, which you can imagine. I will go through them. TPCs, I don't have to explain how they work. Cathode, like in Icarus, there is an electric field. The interaction produces charge and light. The charge is drifted. You need both photomultipliers, photosensors, and charge readout. And then the double phase technique, which I will describe better in a while. For single phase detectors, the advantages I already covered. The disadvantages, you cannot have a particle discrimination in liquid xenon because you don't have pulse shape discrimination, you don't have charge and light, you don't have anything, you simply don't know what is producing the events in your detector, unless you manage to exploit the pulse shape discrimination, which is very difficult in xenon. The position resolution, well, you can have some position resolution because you can use the time of arrival of the photons, and this is done actually in these large size detectors, but it's not very high resolution. And you need a minimum number of photons. So that gives you an energy threshold, which is quite high. While when you measure the charge, as I said, you manage to measure single electrons, and that provides you with a very low threshold. Examples of these huge detectors are both for xenon and for the argon, but the only one which is still in operation is the D3600 detector, which I will show you in the next lecture, because they were surpassed in capabilities by the TPCs. So TPCs, we have huge TPCs for neutrino physics, as I said, thousands of tons of material, of noble liquid. That means only argon, because it's impossible to do such a huge detector with xenon. It will be very expensive, okay? And there is not enough xenon. It's very useful to record the tracks because of this D over the X capability. So it can also do particle discrimination on the basis of dA over dx, and it is in fact used for neutrino physics. So the Dune experiment is completely based on these liquid argon techniques, both for the far detector and for the new detector. The charge can be measured with wires, as I explained, but also with many new technologies, which I will briefly mention in my next lecture, in particular pixelated readout, which gives you very high resolution in the reconstruction of the track. And it's also much better from the noise point of view, and from the cost point of view, and from the ease of realization. So very good, or perforated PCB, which is very cheap, and so on. Light readout is done with photosensors with the same problematics that I explained before. Very good position resolution, 3D imaging. These are really imaging detectors, but at higher energies, where higher, I mean above the MeV. In particular, they can be done modular, with a modular design, and this means that you can add up size, which is exploited. You see that these advantages are that you need, in such a huge detector, you cannot measure the single electron, so they have higher energy. I must say that this is not a real showstopper. We are thinking to having these huge detectors sensitive to much lower energy. A lot of R&D is going in this direction. The real problem here is radio purity, because once you will be sensitive to low energy, then you will be flooded with natural radioactivity. So you will also have to select radio pure materials. And the examples are here. There are many large single phase TPCs, but I would like to mention this TPC here, which is the EXO detector. It's a detector for double beta decay that was mentioned yesterday, neutrinoless double beta decay. So we need a very high energy resolution in the MeV region. For this xenon isotope, the Q value is around 2 MeV, 2.2, I think. So that's the energy of the tracks that you have to measure, and you want a very high energy resolution. So you exploit all the things that I have said. You sun, charge, and light, and in fact, here you have both measurement. There is also a big version of this detector proposed for SoUP. So double phase TPC, my last few slides, to introduce my next, the next subject of the next lecture. Okay, I said many times that in dark matter physics, we want to measure very low charge yields, and this means converting, and we use a method to convert the charge into light. Many of you know that this is done through the interposition of a thin gas layer above your TPC. So this is a strong constraint on the geometry of the detector, because in order to produce this gas layer, we use gravity, and this means that you must have a vertical drift. So vertical drift means that you need a cathode here and an anode on the top. So you have your liquid and an electric field inside. Then you produce a small gap of gas, and once the interaction occurs, if you have the electric field, the ionization signal is drifted to the surface, extracted, the electrons are extracted through to the gas phase, and they're accelerated in order to produce proportional scintillation. And the number of photons produced here is proportional to the number of electrons that you have extracted. So provided you have extracted all the electrons, so you convert with again the electrons into photons. And then if you have photons also here, proportional to the electrons, you can use photosensors to measure both the primary scintillation and the secondary electroluminescence signal proportional to the charge, S1 and S2. The problem here that we had to fight many years ago before Marco started to work on this when he was working on MDD was how to read the light signal if we have the electrodes anode and cathode. So one of the very early R&D that had to be done was to provide transparent electrodes. But much road has been done on this problem, and now we have all types of electrodes. In particular, I will mention the idea of having plastic or quartz transparent layers on which you deposit nano layers of resistive materials, and you apply a high voltage to this material with full transparency for the photons. This is done in dark side. This was one of the technologies developed, innovative technologies developed for this physics, which actually made dark side feasible. Disadvantages. It's a complex detector geometry. You have to bring in high voltage through filters, and you have to deal with this level of liquid because you have to have very stable gas phase on the top. So that's an additional cryogenic problem. Okay, so this I already explained. I will only show you a little bit more details about the production of this luminescence signal. Here you see for both argon and xenon the efficiency of electron extraction in the gas phase. In order to do that, you put a grid at a different potential so that you can increase the electric field here with respect to the drift field. Drift field is 20 something electron volt per centimeter in xenon, 200 volt per centimeter in dark side. It's very slow drift. Here you need kilowatts per centimeter in order to be effective in the extraction of the electrons. So this is done exploiting the difference in the electric constant between gas and liquid, and by applying a different electric field in this region, higher electric field. So you need to take this into account. But it's well demonstrated that above a given threshold, which is different for argon and for xenon, another good advantage of argon, one of the few above xenon, is that this electric field is lower in argon than in xenon in order to extract all the electrons and produce the S2 signal. Another thing that you need to take into account is that once you are in the gas phase, you produce the number of photons proportional to the number of electrons extracted with a proportionality constant, the G2, that depends on the operation parameters of your detector. In particular, here you will see the dependence from the electric field, which is necessary in order to extract the electrons, and from the pressure. So this is the triple point, and this is 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, and this is the number of photons that you obtain per electron per centimeter. So this means that my G2 depends on the height of the gas pocket, because this is a number per centimeter. So you want to increase this number, you increase the number of centimeters, and you have more photons. That's why I said it's by design. Then depends on the pressure, but remember that possibly you have the photosensors there. They might be in gas, so you have a high pressure. Your photosensors must be operated in high pressure. Okay? And the electric field, which you need in order to extract all the electrons. You take into account all these, which are parameters, design parameters of your experiment, and you know how many photons you should expect per centimeter and per electron extracted, and then you can compare with the experiment. So finally, once you build this detector, what you obtain in time, this is your oscilloscope, you look at your photosensor signal, for instance, the photomultipliers in xenon, and when the interaction occurs, you will see first a signal proportional to the scintillation produced in your detector, then some time during which the electrons are drifted, and this time is proportional through the drift velocity to the Z, the depth where the interaction, in the detector where the interaction occurred, and you see a huge signal S2 with respect to S1, which is the signal produced by the electrons drifted, extracted, and in some sort amplified when converted to photons. This is an example of event produced by a gamma interaction, so electrons, gamma interacts on electrons, so produces electron recoils, and an example of a similar energy produced by a WIMP. of course, by a neutron producing a recoil in the detector. So it's a nucleus that is moving. And you see immediately that for a given energy, the ratio between charge and light, let's say S2 and S1, is completely different. So let me go back here. The signals S1 and S2, here is an amplified vision in argon, but it's very similar in xenon. And you see that for a given energy, these are similar energy and real data, the ratio between S2 and S1 is much higher for an electron recoil, than for a nuclear recoil. This is the basis of discrimination between electron recoils and nuclear recoils in xenon. In argon, you also have a difference between singlet and triplet, and we have seen that singlet and triplet are populated differently for alpha, nuclear recoils, and electrons. It's slow for a beta gamma, and it's very fast for an electron. This is the scintillation signal, and that's the basis of the discrimination in argon. And the result is this one. So here I have the so-called discrimination power of the two media. A plot taken from Panda X, which is another experiment with xenon, very similar to xenon and Z, which I already mentioned. Here you have the ratio of S2 to S1, and here you have S1, that is the total energy. And this data have been acquired exposing the detector to different sources, known sources. The black points are, I think, tritium decay. The blue point are, I think, neutron interactions obtained either with an ammunition source. Yes, an ammunition with neutron source. They okay, and you see that the two populations are separated, and the separation between the two population depends on the detector, but can reach a discrimination. You can separate a nuclear recoil from an electron recoil with a power which is 1/1000 or even 10,000, not more than that. Okay? Okay. The real thing is percent.
1/200.
Thank you.
That's the.
Okay, so this is the maximum, okay, that you can obtain. That's the maximum. So this means that you really have to remove radioactivity like tritium or any other radioactivity that produces electron recoils in your detector. The discrimination capabilities in argon, in addition to this, because you also have this two in argon, is based on the partial discrimination, the fact that we have different decay constants for the two populations. And you see here a parameter which is proportional to the how fast the signal is. Okay, it's called fraction of prompt light. And you see, and you see that nuclear recoils are separated from an emission beryllium source, are separated from a gamma electron recoil source at a much higher level. Here, the separation power was measured by that side 50 to be larger than 1/100 million. You can identify a nuclear recoil over 100 million events of electron recoils. This was done in that side 50, which was a 50 kilo detector. And then with VIP, which is a much higher, larger detector, they measured more than 10 to the 9, 1 billion events. So it's a huge, the theoretical maximum discrimination power is 10 to 10. So it's a huge discrimination capability that allows us to cope with the internal radioactivity that we have, which is our conservation. And I am back for the moment.
Thank you, Giuliana. I think it was very important to have this very comprehensive introduction, also with the various details, because now we are moving into the detectors, and the details are the key ingredients. Real good experiments work when all these details that she mentioned are spelled out in the proper way.
And
So,
I didn't notice that I'm a bit late maybe on,
not because we decided to have 1:10.
Ah.
Yeah, because you started later.
Ah.
We have time for a few questions, and then maybe we can save the other questions for at the end of the second part of the lecture. Yes, please.
Can you go back to the slide where we have the formula form and you got like
Where we at?
array and the neutron? That's what it is.
Yes. This one?
No,
This one?
no, before my report, like. Yeah. Do you get the same thing on the gamma ray hits first and the gas phase?
Sorry?
If the gamma ray hits first, the gas phase. Do you get the same type of signal?
Yes, the gamma ray occurs, interacts in the gas phase.
Yeah.
So if the gamma ray interacts in the gas phase, you can have a signal, but you will not have this sort of feature. So this is very easily
Yeah.
recognizable.
Yeah, okay, but like, is there some proportionality in the energy you collect between it? It's
We
directly,
simply discard the events that occur in gas phase.
you cannot extract any kind of information from the energy.
Just imagine that the quantity of material that you have in the gas phase is zero with respect to the amount of your detector. And you have to exploit this as one of two features. So there are actually no events there with respect to what you are measuring in the detector.
Other questions? Okay, if not,
Kind of a,
you have a question.
not a question, but I didn't put in the slide and I meant, he made me think of something that I would like to receive a question. I have spoken a lot for 2 hours about how we detect a signal in these detectors, but nobody asked me, what about Cherenkov? It's a basic interaction that we know it will occur. It's actually used in huge detectors for neutrinos when you have water inside of noble liquids to detect all the interactions. And nobody asked, well, what about Cherenkov? We also have Cherenkov here. So that's a good question. Thank you, it's a good question. Yes, we have Cherenkov detection, Cherenkov light. And it is actually used, for instance, in particular, of course, at high energy, because you get a lot of Cherenkov light at high energy, you need to have fast particles in order to produce Cherenkov light. And it is used in neutrino physics to complement the measurements that are done with the scintillation and charge, mostly charge. But Cherenkov light is useful, and is useful also in these dark matter searches in particular. For instance, in argon, it is used to tag particles coming, background particles of high energy, because Cherenkov light is fast. So you can tag it using the pulse rate discrimination and use it to lower the background. So this is done also. Thank you for the question.
What wavelengths does Cherenkov have in argon?
Sorry?
What wavelengths would the Cherenkov have?
Cherenkov light is Cherenkov light, so it's all spectrum of blue down to ultraviolet. It would be blue anyway, blue, detected in blue.
You don't need wavelength shifters for Cherenkov.
Cherenkov you see directly.
We also see benzene.
So for sure it's there. The point is that it's much faint than scintillation light.
Scintillation, Cherenkov in xenon will be very, very, very low. The Cherenkov is produced in particular in the ceramic material. So if you have Teflon, but fortunately then it's also absorbed. We have acrylic, and in the acrylic we have production of Cherenkov, and that Cherenkov also comes in the active region. So it depends on the materials of your detector, but the proportion, you cannot use, you don't want to use it for the energy measurement. It's just a small fraction of the environment. Okay.
Okay, with this we thank
Allora, cambiare una camicia.
And before moving to the lunch break, that anyway will, so that where you know, and we will reconvene at 2:30. Gabriele is putting on the screen
Maybe.
the details to set
Questo
up
qua
your
cambiate.
environment for the hands-on exercises of the statistical lectures that will be this afternoon in the second part of the afternoon. So you can, if you are not yet done with this, you can use the time of the lunch break to be sure that everything is done, because you would like to start sharp, of course, some introduction, but then go on with the others. Have a nice lunch break and see you at 2:30 here.
Noi dobbiamo lasciare come si cambia il monitor? Come si switcha il monitor? Come si switcha il monitor? Ah, no, non mi è successo. Fa così e si fa. È andata. Allora, come lo chiamiamo?
Io avrei una domanda.
Actually, possibly work on like one day, the first half of the day, but after that, it just will be, oh, contact your IT person because you're not licensed or whatever.
Can you try using the local network with another ID?
Login, yeah.
But the point that we cannot reach the login page.
Yeah, but because it doesn't load in the login page, so it's, yeah, but it can on my phone, so that's the part.
Yeah. But we can try maybe with another browser.
I haven't tried that, oh, god, it's.
You have to, I don't know, let's try this way, otherwise you get the certificates.
Yeah, okay, yeah, I can also just try and get the files through a USB on my system as well, that way.
For this, you can maybe get the HTML too.
Let's see. Just HDMI, anything else I should think of?
I don't know who I should
Yeah.
ask. The hands-on session, will it start with exercises or will there be like a part when you talk to us?
Right, no, I'll start with the lectures.
Okay.
Put up the slides now, so yeah.
Okay, okay. No, because
About an hour first and then exercise.
Do you think that we will have exercises also today or not? In the
Yes, I would like to start.
second part.
Yeah, okay. I put up an hour, and I think otherwise, you know, if I just talk for 1.5 hours. it's
No,
ridiculous.
indeed, I also. Is it fine?
No, yes, it's just that I have a meeting at 5, so I was trying to understand if we could do exercises while listening to the meeting, but if it was a real lecture, maybe it's not the case.
That's okay.
Thanks.
Knut, is everything fine
Yes,
for you?
I have my laser, I have my HDMI thing, so everything should be good.
Do you think, what do you prefer? Are you going to present via your laptop?
Yeah,
Or
I have my laptop, HDMI, actually, let's check it first.
we have an adapter?
Oh, nice, I have this guy to do that. Okay, so it's, exactly. Oops.
The only point, it's very easy. I will send you the link to the.
Oh, you put on,
Zoom,
exactly, yeah.
of the,
That's how you get the recording.
yeah, exactly. Oh, I have to stop the recording, by the way. Gabriele, hai già fermato tu la registrazione? No.
Oops. Yeah, let's just check. if everything works.
No, no.
I turn this off. cerchiamo qui sotto.